Hello. In this video, we're going to talk about one of the most fascinating and mysterious objects in our universe, neutron stars.
The formation of a neutron star takes four main steps: a main sequence star, a supergiant, a supernova, and finally a neutron star. Main sequence stars of more than 10 solar masses can form neutron stars. A main sequence star is a star from a specific region in the Hertzsprung-Russell diagram, which is a luminosity surface temperature diagram for stars. This is the region of stars that can go on to form neutron stars. Stars can spend around 10 million years in the main sequence. The main sequence star heats up and expands as it ages, forming a supergiant. As a result of a series of reactions called nuclear burning, the supergiant has an iron-rich core surrounded by outer layers. As nuclear burning in the outer layers slows down, they start to collapse onto the core, heating it up. This leads to electron capture. In this process, the core heats up to the point where the energy of protons and electrons allows them to overcome their repulsion. This causes collisions between the two, producing neutrons and neutrinos, but the neutrino is a type of lepton. This increases the number of neutrons in the core, as well as its density. The core starts resisting the collapse. As a result of electron capture, a flux of neutrinos is produced, causing the layers of the star to explode. This creates a supernova. The heavy core from the explosion is compressed and left. As long as its mass is lower than 3 solar masses, the core forms a neutron star.
Just like any other planet, neutron stars contain an atmosphere, a crust, and a core. Its atmosphere is primarily made up of hydrogen and helium. The surface is very smooth due to the high surface gravity, and sometimes the surface can contain iron. The inner and the outer crust contains a range of particles like free electrons, ions, neutrons, and nuclei, where these nuclei have large quantities of neutrons that would instantly decay if not for the high pressures in a neutron star. They contain charges like electrons, and due to its extreme rotational speeds, this contributes to its enormous magnetic fields. The outer core contains liquid forms of neutrons, protons, and electrons due to the increasing pressures inside. The inner core, with the highest density and pressure, still remains a mystery. One theory is that the subatomic particles like neutrons and electrons break up into quarks, but nothing is known.
Here comes to the properties of neutron stars. The mass of a neutron star ranges from 1.1 to 2.1 solar masses. The upper limit of the mass is called the Tolman-Oppenheimer-Volkoff limit. Since neutron star is only a small part of its parent body, retaining most of angular momentum, it forms at a very high rotational speed and then slowly decelerates. The density of neutron stars increases with steps. Its overall density is still extremely large and very close to the density of the nucleus. The huge density also gives it a very high surface gravity, causing the escape velocity of neutron stars is about 1/3 to half of the speed of light. Its gravitational force is so strong that the light will be bent when passing through, named gravitational lensing. The neutron star is very hot, and the temperature inside the newly formed neutron star is about 10 to the power of 11 Kelvin. The large number of neutrinos it emits has taken lots of energy, so the temperature of the neutron star drops to about 10 to the power of 6 Kelvin within a few years. The magnetic field strength on the surface of neutron stars is also very high, and the variations in the magnetic field are the main factors that allows different types of neutron stars to be distinguished by their spectra.
In 1967, Jocelyn Bell, a Cambridge student, discovered rapid variations of radio signals while studying distant radio sources with a special detector built by Anthony Lewis, called Interplanetary Scintillation Array. The pulses arrived roughly every 1.35 seconds, and they were regular, sharp, and intense. She thought she may have discovered an intelligent civilization, jokingly named the source as Little Green Men. However, what they have found was nothing but actually a neutron star rapidly pulsating radio waves. Since neutron stars emit electromagnetic radiation from their magnetic poles and highly magnetized, this enabled astronomers to detect these pulsars, acronym for pulsating radio source, with radio telescopes. which by today we have detected around 2,500 of them. Later in 2017, the light and gravitational waves from the collision of neutron stars arrived to our planet. The gravitational wave was detected by Laser Interferometer Gravitational Observatory. An interferometer is a sensitive instrument that can detect the changes of space-time by observing the changes of interference pattern produced by two light sources. As you can see in this animation right now, which is done by NASA and Georgia Tech, two neutron stars are rotating around each other, which causes space-time to squeeze and produce gravitational waves, as you can see right now. As they merged, a fireball of gamma radiation was produced, which was picked up by the Fermi Gamma Ray Telescope. The left-behind materials started merging with nuclear reactions, which is an event called kilonova. A matter like iron and gold produced by this event rained over the Earth. This way, we detected colliding neutron stars for the first time ever.